Hey everyone, my name is Jacob Lynch, and today I'm excited to share a cool recent discovery in chemistry. One that defies the traditional rules and opens up new frontiers in organometallic science. We'll explore the discovery of Berkelocene, the first known organometallic compound featuring radioactive element berkelium. What is Berkelocene? Berkelocene is an organometallic compound where a berkelium atom is bonded between two cyclooctatetraene rings. If that sounds familiar, it's because the structure mimics the famous compound ferrocene. But unlike ferrocene, which contains iron, Berkelocene uses berkelium, a rare and highly radioactive actinide. Who did this? This incredible work was done by a team of chemists at Lawrence Berkeley National Lab and UC Berkeley. They managed to synthesize this compound using just 0.3 milligrams of berkelium-249, a tiny amount because berkelium is extremely rare and radioactive. The research was recently published in Science and drew attention for publishing the limits of synthetic chemistry. Why it's important. This figure shows the highest known oxidation states for each element in the actinide series. As you can see, most actinides like americium and curium stabilize at +3. A few like uranium and neptunium can reach as high as +6 or +7. What makes this discovery so important is that berkelium, which sits in the middle of the series, was thought to behave like the lanthanides and primarily form +3 oxidation states. But here, scientists successfully stabilize berkelium in the +4 oxidation state in a real molecule, Berkelocene. That had never been done before. This isn't just a new compound, it's a breakthrough that changes how we think about actinide chemistry. Understanding and controlling oxidation states like this is key for developing better nuclear waste management strategies, designing new materials, and refining our theoretical models of F-block chemistry. So this image helps explain why Berkelocene is such a big deal. It shows berkelium standing out in a way no one fully expected. Why I find it interesting. I find this research fascinating because it blends precise experimental work handling radioactive substances in air-free conditions with deep theoretical modeling. It's not just making a new compound, it's changing how we understand a whole section of the periodic table, which I've always been fascinated in learning more about. It also shows that even unstable exotic elements can form elegant, well-defined molecules. Connecting article, rule-breaking ferrocene. To show how this fits into a broader trend, let's look at a second study from 2025. Scientists in Japan synthesized a stable 20-electron ferrocene derivative. This breaks the famous 18-electron rule, which says organometallics are most stable with 18 valence electrons. With Berkelocene, this compound defies our expectations and pushes the boundaries of what's chemically possible. Shared themes. Both discoveries share key themes. They each challenge long-standing assumptions in chemistry, and they open up new paths in organometallic design. One uses a heavy radioactive actinide, the other uses iron, but in a completely unexpected way. Together, they show us that chemistry still has plenty of surprises and rules are made to be rewritten. Why it matters in the big picture. Berkelocene isn't just a curiosity. It teaches us how to better understand and control F-block elements, which are central to nuclear energy, medicine, and defense. It also shows that even complete fields like organometallic chemistry still hold surprises. Chemistry is not static. It's constantly growing, and discoveries like this keep it vibrant. Here are the sources I used for today's presentation. These include primary research article on Berkelocene and a second study on furacene from OIST, along with a few summaries from reputable science news outlets. So thank you. It's been fun in this class. I've had fun doing the experiments, and I appreciate it.